Black holes, some of the most destructive objects in our universe, able to swallow whole stars and inescapable for anything and everything, including the fastest thing in our universe, light. Even though no objects or even information can escape a black hole, energy can still be stolen from them in a way you may not expect, rotation. Black holes are the densest regions in the universe, and the point where the curvature of spacetime causes a self-sustaining hole. Fun fact, black holes don't actually require any mass to exist, and the curvature of space it causes will persist even if the mass inside the black hole is removed. If you want to know more, look up Schwarzschild metric on Wikipedia. Most black holes we know of are the collapsed remnants of giant stars ranging in size from tens to hundreds of times the mass of our Sun. There are also supermassive black holes, which are the size of our solar system and exist at the centers of galaxies, like our own. Because black holes come from stars which are spinning, the black holes that form when those stars collapse must also be spinning due to conservation of momentum. The angular momentum of a star ends up concentrated in an area much smaller than the original star, therefore causing the black hole to be spinning really fast. Think about it like one of those spinning office chairs. When you spin around and pull your arms in, you go much faster. This speed stretches the black hole about its equator, and also creates what we know of as the Ergosphere, a toroidal, donut-shaped region of space dragged along by a black hole faster than the speed of light relative to the outside universe, forcing everything near the black hole to spin as well. This spin is what allows us to steal energy from the black hole. If you sent a particle on a path through the ergosphere around a black hole, and broke it into two pieces so one part falls back into the black hole, that other half's trajectory would allow it to leave the ergosphere with much more energy than when it entered. This concept can also apply to waves, such as light, in a phenomenon called superradiance. Superradiance is the same idea as the Penrose process, where some of the wave is lost into the black hole, while the rest of it is shot out with a much higher energy than before. Recently, this idea of waves stealing energy from a rotating medium has been tested with promising results. In a paper published in the journal Nature, an acoustic analog of waves taking energy from a rotating black hole was created and used to test superradiance. When the machine was spin up, the frequency of the wave after passing through it dropped and eventually went negative, at which point it began being able to pick up energy from the rotation. They showed that the presence of an absorber of the sound, which acts like the event horizon of a black hole, combined with the rotation, causes the sound coming out of the apparatus to be amplified by 30%. For current humans, the utility of the Penrose process and superradiance is limited, as we are unlikely to be dropping stuff into black holes for energy anytime soon. But, for far future theoretical space-going species who need a boost for their spacecraft, the ergospheres of large black holes give them the boost of power needed for their journeys to explore the galaxies.